The magnitude of the force depends on the strength of the magnetic field. In this case, flux density is a dt slab. The current flowing in the conductor current is I ampere, and the length of the conductor in the magnetic field is less than L. So in this case, we can calculate F to be BIL. So in this case, B is the magnetic field intensity, I is the current, L is the length. So the force can be calculated BIL Newton. Calculate the force acting on a 200 millimeter less on the conductor carrying the 30 ampere current at the right angle to the magnetic field of the point for the Tesla. What do we know is, we know there is a 200 millimeter current 30 ampere plus density 0.4 Tesla. What do we want to know? F is the BIL. So the 0.4 minus 30 minus 200 minus 10 power minus 3, you got the 2.4 Newton. So in this case, this is for the north pole and south pole, the magnetic flux are firing. In this case, the conductor moving like this. The current are flowing like this, and this is conductor moving like this. So it can happen a weaker magnetic field and a stronger magnetic field, then it can happen the force. So this is the magnetic field direction. Also, current flow in the conductor, and you can see the indicate the weaker and the stronger magnetic field, and the motor will be rotating the direction. So this is for the direction principle of the magnetic field and current direction, and the magnetic field around the current carrying conductor, and the direction of the position of the weaker magnetic field and strength of magnetic field, and the rotational force. So this is the rotation with the direction. So this standings are for it depends on the conductor. In this case, the force and the radius multiply, you can calculate the torque. Torque can be calculated. So this is the torque, this is rotation. Torque equal to force multiplied radius. The unit is a Newton meter. So the torque equal to VI multiplying R. B is the flux density, I is the current, A is the length of the conductor, R is the radius. We have to calculate a single loop armature winding on the DC motor has a diameter of 520 millimeter, a length of the 180 millimeter, and carries the current of the 15 ampere in a magnetic field of 1/1 Tesla. We need to determine the force developed on the one half of the loop, the torque developed on the one half of the loop, and the torque developed by the armature. What do we know? In this case, the D is a 520 millimeter, A is a 180 millimeter, I is a 50 ampere, B 1/1 Tesla. If we go to BIL, so the 1/1 minus 50 minus 1/18, you got the 2.97 Newton. And the T is equal to FR, so I is 260 millimeter, so 2.97 minus 2.6, you got the 0.7722 Newton meter. So this is for the torque. The torque developed in the one side of the armature is also developed on the other side. So that the total torque developed on the armature for 1 tower of Y has a twice that developed on the conductor. So this is the ways that we calculated. So T is a 2T1. So that will be the 1/44 Newton meter. So this is the way we calculate the torque. So in this case, a more practical approach to torque uses motor output. This is a rotational speed. P equal to omega T. In this case, omega is 2/n/6T. And this is a revolution per minute. T is a torque. So the 2/n is a rotational speed of the motor in radian per second. We need to calculate the torque developed by the motor. That developed and the output of the 4/2 kilowatt, output and 1100 RPM. So what we know is P is a 4/2 kilowatt and is a 1100 RPM. What do we want to know? P equal to 2/n T by the 60. You got a T equal to 60 P by 2/n. So you can calculate 36.46 Newton meter. When the motor armature rotates, it has a current induced into it by the generator action. So the generator EMF output is applied voltage. So the generator EMF is called the counter of back EMF EG. So this is a motor acting as a generator. We can use a sum motor. So this way the shunt and the compound separately excited DC generators diagram. Here is the series DC generator. And here is shunt and the compound. This is a separately excited machine, series machine, shunt machine, and compound machine. So this is where we can draw this diagram. So the motor acting as a generator, we can use a model. So EG equal to KE into 5M. In this case, the K is a constant. In this case, the applied voltage is larger than the generator voltage. The VD equal to IAI plus EG. So the armature current can be found in this RA equal to BD minus EG divided by RA. For a given motor, torque is proportional to the plus 5 armature current IAN, element of machine construction, which is constant KD. So the T equal to KD to 5A. P equal to omega T, 2 by N T by 6T, so you got the EGIA. So that 60 EGIA divided by 2 by N, so the EG equal to ZB 5 N by 60A. So then we calculate it. So that will be the ZB 5A 5, 2 by A, so the KTIA into 5. The machine constant for the torque calculation already takes into the consideration. Number of pole P, number of conductor Z, and they are passed through the magnetic PA. So the machine constant for the calculating generator voltage is not the same as the machine constant for the calculating torque. So E is equal to ZV 5 and divided by 60A, so K equal to PZ by 60A. So then you calculate that T equal to ZB 5 IA by 2 by A, KT equal to PZ by 2 by A. So the 60 K equal to 2 by KT, so the PZ by A. Automatic torque control is as the mechanical load increase, armature speed decrease. So the back EIR decrease. So the EG equal to KE5 and EG decrease, so the, in this case, armature current increase because of the IA equal to BD minus EG by IA. So that when the mechanical load increase, what happens is that armature speed decrease, back EIS decrease, armature current increase. Motor torque also increase because of the T equal to K5, KD5 IA. The armature speed will adjust itself until there is a sufficient armature current IA to provide the necessary torque to drive the load or the machine stop. We have to calculate if 4 volts DC motor has a torque machine constant of the 80, carries a armature current of 25 ampere and operate with a P plus of the 0.016 volt. Determine the torque developed by the motor. What do we know is N equal to 4 volts, K equal to 80, I equal to 25 A. So the pi equal to 0.016 volt. What do we want to know? T equal to KD5 IA. In this case, 60 into 0.016 into 25, you got a 32 and Newton meter. Determine the torque developed by the motor if it has a load applied to such that the armature current increases to 35 ampere. So the IA to 35 ampere equal to KT5 IA, so that 80 minus 0.016 minus 35, you got a 44.8 Newton meter. The next problem. A 350 volt squarely excited motor has an effective P plus of the 0.08 Weber and operates at the speed of the 500 RPM. If the motor has a generation the machine constant of the 15 and armature resistance of 0.250, we need to determine the back EMF, armature current, and the developed torque. What do we know is VD equal to 350 volt. So the supply voltage 350 volt, they are SAEG. So the 5 equal to 0.08 Weber, N equal to 500 RPM, K equal to 15, R equal to 0.0250. What do we want to know is that E equal to KE into 5M, so the 15 into 0.08 into 500, E equal to 300 volt, I equal to VD minus EG by R equal to 650 minus 300 divided by 0.25, you got a 200 ampere. The torque developed, torque is a 60 KE, 5 IA by 2 pi. So 60 minus 15 minus 0.08 minus 200 divided by 2 pi, you got a 2291.8 Newton. Then you have to do that practical exercise. So this is a DC motor car, so this is for the Fleming Lehman rule. Depending on the current flow and magnetic field plus direction, motor will be rotating. So in this case, the dot means a current flow to what? Cross means the current flow away. So this is the magnetic field direction and the dot. At the end of this session, students should be able to list the three main types of the DC motor, draw the circuit arrangement and the connect the various DC motors, state the typical application for the types of the DC motor, describe the operating characteristic of various types of the DC motor, the vast direction or rotation of the DC motor, calculate the value of voltage, current, and torque associated with the DC motor. DC motors are classified according with their P-winding connection. The same as the generator can be used with the same motor. So this is a straight excited DC motor, here is shunt DC motor, series DC motor, and a compound DC motor. This is a long shunt compound and a short shunt compound DC motor. Long shunt and short shunt compound DC motor. Generator, we use a 4-in connector. So this is the primary right hand loop for the generator, plus motion and the current. And motor, you use a primary right hand loop. The action of the DC motor and generator depend on the mutual electromagnetic induction. DC motors are generator converts the mechanical energy to electrical energy. DC motor converts the electrical energy to mechanical energy. Shunt motor, applying voltage VD constant, IF and phi are relatively constant. Low change, motor speed will change. The BF, that year will change because of the EG will KE and phi. And armature current IA will change and the torque will change. So IA will be minus EG by IA equal to KD phi IA, causing the speed to change back to original value. Shunt motors are considered to be constant speed. Shunt motor characteristic, follow here armature current. So this way the shunt motor characteristic. Shunt motor characteristic, all those are armature current changing, speed will not change too much. Percentage regulation is a no load speed minus full load speed divided by full load speed. Percentage regulation is no load speed minus full load speed divided by full load speed. In this case, our DC shunt motor has an over circuit speed of the 200,500 RPM, which reduced to the 2450. When the motor is providing a rated current, calculate the speed regulation. In this case, percentage speed regulation is 250 minus 2450 divided by 2450 into 100. You got a 2%. This is the shunt motor characteristic, armature current, full load current. In this case, torque characteristic. This is the efficiency. So this is a graph of the speed, efficiency, and the torque. We have to calculate a 250 volt shunt motor draws a line current of 20 ampere. Calculate the back EMF. If the shunt field resistance is 200 ohm, the armature current circuit resistance is 0.2 ohm. So in this case, this is the connection of the shunt motor. This is shunt motor connection. In this case, IF will be by R to 250 divided by 200, 1 by 25 ampere. IA will IL minus IF to 20 minus 1 by 25, you got 18.75 ampere. EG equal to VD minus IARA. There's a 2. So we calculated EG equal to 246.25 ohm. 4. You have to calculate the use of back EMF with the load current change to 25 ampere. The load current change IA to IL minus IF equal to 23.75 ampere. E equal to VD minus IARA. So that then we got the EG equal to 245.254. Series motor is a applying voltage VD relatives are constant, but IA and phi are variable and related. If there is a no load motor speed and will be very high because there is a no IA and little phi, residual magnetism, only the load change, the speed will change, and back EMF will change. So EG will KE into phi. Armature current IA will change, IA will VD minus EG divided by IA, and also the torque will change, D to KT into phi IA. Series motors are considered to be variable speed. There is a shunt motor characteristic, full load current, armature current here. This is torque direction and this is speed. So this is the armature current, speed and torque characteristic of the shunt motor. This is the efficiency percentage. We have to calculate the line current drawn by the 400 volt series motor with an armature circuit resistance 0.4 ohm and back E and 360 volt. So in this case, this is the 400 volts are 2.2 ohm and 0.2 ohm at 360 volt. So IA equal to VD minus EG by RA, so that the 400 minus 360 by 0.4, IA is 100 ampere. We have to calculate the U back EMF if the line current change to 125 ampere. IA is 125 ampere, EG equal to VD minus IA is 400 minus 125 into 0.4, you got the 350 volt. Compound motor, a combinated compound motor, series and shunt field assist each other. Like series winding, characteristic of the shunt motor but the better torque. Heavy series winding, characteristic of series motor but better speed regulation on the right close. So those are the characteristics of the combinated compound. They are series and the shunt field windings are assist each other. Like series field winding, they're similar to the characteristic of shunt motor, but the better torque. Heavy series winding. Characteristic of the series motor, better speed regulation on the right load. Compound motor characteristics is that this is a output speed torque and a low current MBR, rated body level compound, over compound, and under compound. Those are the level over and under compounds of motor characteristics. Compound motors are cumulative compound motor applicable into the constant speed by the gradient load, pressures, planar, compressor, and this. They are possible intermediate overload situation. Differential compound is a series and shunt speed opposite each other. Water speed tends to increase with the increased load. Water speed fluctuation under the changing load. Very few applications they use where the motor speed critical, but have the almost being superseded by the shunt motor. Calculate the line current drawn by a 240 volt compound motor with a shunt speed resistance of 120 ohm, CV resistance of the 0.3 ohm, and the armature resistance of 0.5 ohm. If back the EMF is 220 volt. So then you see the 220 volt, the 0.3, 0.5 ohm, then 120 volt. So in this case, IA, VD minus E by RA, 240 minus 220 minus 0.3 plus 0.5, you got a 25 ampere. I equal to VD by RT, so then you got the 240 by 120, you got a 2 ampere. IA equal to IA plus IF is a 27 ampere. We have to calculate the new back EMF when the line current change to 32 ampere. IA is 32 ampere, IF is 2 ampere. So then for IA equal to IM minus IF, you got the 30 ampere is equal to VD minus IRA. Then the 240 minus 30 into the 0.8, you got a 2164. Loss and efficiency, power in and power out. Machine 100% efficient if the power out is the same as the power in. And going to be out by B in. Then the loss and efficiency, but machine has a losses. In this case, our power out will be less than the power in. Fixed losses can be the friction and winding losses, iron and the iron loss. Those are the fixed loss. Due to the construction and physical characteristics of the machine, fixed losses happen. The variable losses are the copper loss because of the depending on the I square R. Due to the operation of the machine, I square R losses are the copper loss. So therefore, the power in minus are fixed loss and the copper loss. Then we got the power out. The power out is the efficiency can be calculated. In this case, our losses can be the iron, friction, windage, or the copper loss, and equal to P out by P. Maximum efficiency occurs when the fixed loss equal to variable loss. Rotational reverse. To reverse the direction of the rotation of the DC motor, the relationship between the magnetic fields in the magnetic field winding and the armature must be reversed. To reverse the direction of the rotation of the DC motor, the direction of current flow in either the field winding or the armature must be reversed. So this is a series motor connection diagram here. The chain of the field and the chain of the armature. Shunt motor, chain and when the chain of field, direction will be rotation. So that you can change the field winding or chain armature winding. Compound motor, change the field or change the armature. Then we have to do the practical exercise. So this is a DC motor static and specialist machine. DC motor are classified across with their P winding connection. Let's say the generator, we use the same motor. So this is these are excited DC motor, series motor, shunt motor, and compound motor. Long shunt compound, short shunt compound machines. And this is the shunt motor characteristic speed. Armature current, torque, efficiency, and speed characteristic of DC motor, shunt motor. And this is a series motor characteristic, armature current, efficiency, speed, and the torque. Then compound motor characteristic, regular body, level compound, full current, over compound, and level compound, under compound direction. So this is a reverse. Before the reverse, also the field of the chain or current, motor rotation can be changed. So you can change the field connection or the armature connection. Motor rotation will be changed. Also the losses, this is the losses and efficiency diagram. friction, iron loss, copper loss, and input power minus output power, efficiency power output by power input. At the end of this session, students should be able to explain the need for the current limited in the DC motor starters, calculate the value of starting resistance for a given DC motor, describe the construction of torque, turbo generator, servo motor, and stepper motor, explain the operating principle of techno generator, servo motor, and stepper motor, and list the application of the techno generator, servo motor, and stepper motor. In this case, at the start of the motor armature current is a maximum because the back here is 0 at the start of motor armature current must be limited to protect the machine. Armature current usually limited to the 150 to 200% of the full load. Calculate the resistance necessary to limit the starting current of 300 volts for all motors to the 150% of the is a full load current. If it has a shunt field resistance of the 1,200 ohm, the armature resistance of 1 ohm and the rated full load current of 23 ampere. So in this case, this is a shunt field and the armature current shunt field and the CDP winding supply voltage and the IS 150% of IA 1.5 into the 24.5 ampere. IF equal to VD by RT, so that's 600 by 1200, 0.5 ampere. I equal to IS minus IF, so that's 34.5 minus 0.5, equal to 34 ampere. Armature resistance is a VD by IA can be calculated, so the 600 by 34, you got a 70 by 65 ampere. RS equal to R80 minus RA, you got a 70 by 65 minus 1, you got a 16 by 65 ohm. Calculate the resistance necessary to limit the starting current of 240 volt, shunt motor to the 150% of the full load current. If it has a shunt field resistance of 480 ohm and armature resistance 0.5 ohm and rated full load current of the 45 ampere. Then you can calculate this is for the direction of the motor, connection of motor, armature and shunt field resistance, input current 240 volt, IS 150% of IA, so that 1.5 into 45, C7.5 ampere. IF will be by RT, 240 by 480, you got the 0.5 ampere. I equal to IS minus IF, you got there, so 67 ampere. C7.5 minus 0.5 of 67 ampere. R80, V80 by IA can be calculated 240 by 67, you got the 3 by 58, and then 3 by 5 minus 5, you got the 3 ohm. The next one is calculate the resistance necessary to limit the starting current of 250 volt series motor to the 150% of full load current. If he has a series field resistance of the 0.1 ohm, armature resistance 0.067 ohm, and rated full load current of the 100 ampere. Then so that 250 volt supply, and current is supply 100 ampere, the series field resistance 0.167. Then IS 150% of the IA, so that 1.5 minus 100, you got a 1.5, 150 ampere. I equal to IS, RAD VD by IA, so 250 and 150, you got a 1/67. Then RS with RAD minus RA, you got a 1/67 minus 0.16, you got a 1/50. Especially DC machines that we can see that the taco generators are easy the direct proportion to the speed. Taco generator is an armature speed and there's an output terminal voltage. EG got equations are K into pi into M. So armature speed higher, output terminal voltage higher. This is a construction that we use for the generally small machine and also permanent magnet. The applications are that we use for the direct speed measurement, speed sensor in the control system. So the taco generator are the EG is the direct proportional to the speed. They use for the stepper motor, convert the electrical power into mechanical motion. So this is the connection of the stepper motor diagram. Stepper motor, this is the switch connection, and where the rotation can happen like this. So this is stepper motor's operating diagram. The specialist DC machines are the taco generators are generator voltage is proportional to the speed. Stepper motor converts the electrical power into mechanical mode. Moment servo motors are the converts the electrical signal to mechanical movement. So this is a control unit driven by the servo motor. Then you have to do the practical exercise. So this is for the electrical trade. Regarding the advanced diploma electrical engineering, you have to study the following. So electrical diploma 2022. Then you do the video lesson. YouTube video electrical engineering lesson. Then complete the lesson. So what you have to do is that you have to do the industrial process control. So IWC06 are process control. Process control systems are those are unique here. You have to click this highlight computer.com/video lesson.html. So 42592 Read the 429-472, and those are the lesson video and notes are here. So you have to read through this notes and also read the lesson video. Then you also continue the solar electrical system. Solar electrical system page 473 to 490. Those are the notes, and also view the video and read the lesson. And also the grid connected inverter. So the page 491 to 501. So then you have to view those video, and also the energy efficient building design. So page 502 to 528, and you have to view the dual lesson. Do the lesson and do the exercise. So those are all the electrical engineering, advanced diploma electrical engineering lesson. Those you have to do it. Regarding the electrical trade, electrical trade 2022, we go here, and I also provide you with the programmable logic controller. If they go down, programmable logic controllers are here. We click as a programmable logic controller. So here I give you the PLC textbook. PLC textbook you need to download. So SCADA manual, PLC textbook, and also here you can see the PLC video. Those videos are the PLC full lecture, basic PLC, typologies are also PLC programming, set and reset timer, PLC simulator, PLC program, counter, chip register, PLC instruction timer processor, as well as the SCADA system. SCADA system, you can also download the notes. So this is the PLC system. Similarly, we also provide with the user with a programmable logic controller. So here you use a PLC textbook, PLC basic teaching guide, and students are assignment, students are SCADA, who are seated SCADA, and also project. And also I provide you with the PLC hardware and the software node. Really setting up of the PLC application, also the process control unit setup. Those are also provided. So therefore that you also read through the programmable logic controllers lesson. Also that they are practical. Also you can also do the appropriate lesson and also video. Those are also provided for the programmable logic controller.